Hello everyone, today we're going to go over Leetcode problem number 72, edit distance. This is a hard problem, but I think it shows up very often in programming interviews, so I just wanted to go over what the solution would look like. So here's the problem description. Given two strings, word1 and word2, return the minimum number of operations required to convert word1 to word2. And you have the following three operations: inserting character, deleting character, and replacing character. So the optimal solution for this problem actually uses dynamic programming. And I'm going to go over the concept first on the right-hand side, then start coding on the left-hand side. So let's begin. Okay, so we're going to build up from one example. Namely, we're going to transform from word1, horse, to word2, Ross. In order to do this, we're going to set up some helper variables where m is equal to the length of word1 and n is equal to the length of word2. In order to tackle any dynamic programming problem, we have to consider what the subproblem is. So the subproblem in this DP problem is that we want to find the minimum edit distance between 0 to I in word1 and 0 to j in word2. Basically, we're taking a portion of word1 and trying to convert it to a portion of word2. And that portion can actually be the entire word1 or the entire word2, or even none of it. So now that we have our subproblem defined, we have to look at what the DP table is going to look like. We're going to have an n plus 1 by n plus 1 DP table. And it's n plus 1 because that's how many characters the first word has, plus 1 for basically an empty word. And the same can be said for the number of columns, right? Because it's n, the number of characters that the second word has, plus 1 for the empty word. So just a reminder, when you're programming the solution, be careful of your indices, because it's very easy to get stuck in off by 1 errors. In any case, let's remember our goal. Our goal is to fill in this DP table until we get to the bottom right here, because dpmn is our answer. Remember that this DP table is basically storing the answers to the subproblems that we've defined. So dpmn is not just a random cell in a matrix, it means what is the minimum edit distance needed to transform horse to Ross, right? The fact that we are looking at cell mn means that we're including the entirety of word1 and the entirety of word2. Now, we have to first start from the most easiest cases in a dynamic programming solution. So the most easiest case is if I equals 0 and j equals 0. Here, I and j are merely indices that are used to iterate through each character in word1 and word2 respectively. So I belongs to word1, j belongs to word2. So if I equals 0 and j equals 0, we're basically asking what is the minimum edit distance to transform from empty word1 to empty word2. Well, you're already there, so the answer is obvious, it's 0. Now what if I equals 0 and j goes from 1 to n? That's asking what's the minimum edit distance to transform from empty word1 to r, empty word1 to row, empty word1 to Ross. And that is just 1, 2, and 3 respectively, because all you can do here is just insert the appropriate number of characters. Now, what if j equals 0 and I can go from 1 to m? Well, that's just asking if I have h, what's the minimum edit distance to transform that to the empty word2, or ho to empty word2, and so on and so forth. And you see, it's 1, 2, 3, 4, and 5, because we're literally just deleting the appropriate number of characters. So these are very easy examples that we can solve very quickly. And after that, the DP table looks very good, meaning that we only... Excuse me, let me say that again. So after we've solved all these base cases, we know that the first row and the first column have been completely solved. We don't have to worry about them anymore. we now have to go through this DB table and start filling cells in that haven't been filled in until we get to the bottom right corner, which is our goal, our destination. So that's what we're going to do with this double for loop. We're going to say for I equals 1 to m, for j equals 1 to n, we're going to check for these two cases. Now, case 1 means if the current letter we're at in word 1 doesn't equal the current letter we're at in word 2, then we're in case 1. Meaning that if E here doesn't equal S, which it doesn't, right? They're not the same character, then we're in case 1. So this is one example of being in case 1. Else, we're in case 2, meaning that the characters we're at are actually matching. And this would be an example. Ho and Ro, basically O and O match, so we're in case 2. But let's look at case 1 first. In case 1, we know that the character we're at in word 1 doesn't match the character we're at in word 2, so we have to do some kind of replace, insert, or deletion operation. But which one do we do? Well, we do whatever is the minimum cost. How do we know what the minimum cost is? Well, we just consider all possible scenarios and take the minimum. So let's see what happens when we do a replace operation. Step 1 is first to solve the subproblem hors to row. And the answer to that is just dp I-1, j-1. Then we would have, in step 2, row to Ross. Now it's just as simple as replacing E with S. And you've solved the problem. The overall cost here is dp I-1, j-1 from step 1, plus 1 from the replacement operation you did in step 2. For the insertion operations, very similar. We want to solve the subproblem horse to row. And the answer is already calculated for us. We already did that in the past, so we're just going to look into our DB table and fetch it. No complicated, very time-consuming calculations. So it's just dpi j-1. Now we have row to Ross, and we just have to insert s. Overall cost is this. For a deletion operation, we solve the subproblem hors to Ross. Again, it's already in the DP table, and then we have rows to Ross, just delete E, and the overall cost is dp I-1, j plus 1, right? So we have the cost of all these operations. We're just going to take the minimum, and we're going to set dp ij equal to that minimum cost. Now in case 2, if the characters are actually equal, then all we have to do is look at dp I-1, j-1. Because the characters are already matching, we can just cut them off and say that the answer is equal to the two words without those characters. Now, after this double for loop, this is what the DP table is going to look like. Now, I just want to quickly go over how we would actually perform this algorithm by hand, because it might give you a visual indication of what we're actually doing when we write this code. So let me just reset this table very quickly. I'm just going to reset it to what it was before we ran this double for loop, but after we calculated all the base case cells. So it's going to look like this. Right, so we finished with the first column, first row, and we're starting at coordinates 1, 1. And we're going to see, does H match R? It doesn't, so we're in case 1. So does that mean we do a replacement, insertion, or deletion? Well, we are either looking to the left, upwards, or diagonally. And we're going to take the minimum, which is 0, and add 1 to that. So that's going to be 1. Next. Does H match with O? Does not, so minimum, which is 1, plus 1 is 2. Next, does H match with S? It does not, so minimum is 2 plus 1 is 3. Next, does O match with R? It doesn't, so minimum plus 1 is 2. Does O match with O? It does, so we're actually going to look diagonally, which is 1. Diagonally up and to the left is what I mean. Now, does O and S match? They do not match, so it's minimum plus 1, which is 2. Now, do R and R match? They do match, so it's going to be diagonally. Do R and O match? They do not match, so it's going to be minimum plus 1 is 2. Do R and S match? No, they do not match, so it's going to be minimum plus 1, which is 2. Okay, so I'm going to go a little faster now since we probably know the pattern at this point. So S and R do not match, so it's going to be 3. S and O do not match, so it's going to be 3. S and S match, so it's going to be 2. E and R do not match, so it's going to be 4. E and O do not match, so it's going to be 4. And E and S do not match, so it's going to be 3. Okay. Now, notice our final step is to return dpmn, which is basically 3. And we know that that's correct because it's one of our examples. The output should be 3. So that's basically the conceptual overview. And let me show you how easy it is to convert this concept to code based on everything I've laid out so far. So let's say we have m equals length of word 1, n equals length of word 2. Now we're going to set up our DP table. It's going to be a 2D matrix, and we're going to say for j in range plus 1, and for I in range n plus 1. So that's going to be our DP table, and we're going to move to our base cases now. So the first base case is already taken care of because we initialize everything to 0 anyway. The second base case is what we have to code. So for j in range 1 to n plus 1, we're going to say dp of 0 to j is equal to j. And for the third base case, we're going to say for I in range 1 to n plus 1, dp of I 0 is equal to I. Now we're going to look at our double for loop. For I in range n plus 1, for j in range n plus 1, we're going to check for case 1 or case 2. So line 48 says, if word 1, I minus 1, does not equal word 2, j minus 1, then we're in case 1. What does case 1 do? We're going to check all possibilities. Replace cost is going to be equal to dp I minus 1, j minus 1, plus 1. Insert cost is going to be equal to dp I, j minus 1, plus 1. Delete cost is going to be equal to dp I minus 1, j plus 1. The minimum cost is going to equal min of replace cost, insert cost, and delete cost. And then we're going to say dp I j is equal to min cost. Now, otherwise, we're going to be in case 2, which means that dp I j is just going to be dp I minus 1, j minus 1. And the very last step in line 77 is just to return dpmn. All right, let's see if this works. Let's see. We have string index out of range here. So again, you have to be very careful with your indices. I see. So we actually want to include the beginning indices here, right? Because if we start at 0, 0 minus 1 0 minus 1 would not be great. That would be negative 1. Anyway, if we include the starting indices here, it should work. Let's see. Okay. So here are the stats if you're interested. but essentially we've solved the problem. The code is actually pretty simple once you know the concept, but this is a hard problem because there's so many steps involved in figuring out the solution. The time complexity here is big O of mn because we're basically filling in a table that is of size mn. Space complexity, big O of mn, because again, we have a table of size mn, roughly mn, m plus 1, but roughly mn. Okay, so this is basically the solution to this problem. If you have any questions, please or well, if you have questions, please comment. But otherwise, if you like this video, like and comment and subscribe. But I think that's it. Thank you for watching, and I'll see you in the next one.